So so this is basically sampling the triangular distribution to get delta V. And one of the things is that through the sampling, I actually have changed the number of samples. So let me just modify the number of samples to the length of delta V, right? So because I have rejected part of these samples. So that's the new number of samples, and we want to use these samples, these many samples, to sample my the time of the burn, so t. Okay, so t is an exponential distribution. So how do we sample such an exponential distribution? Right, so we know we have used a acceptance rejection for delta V, which is triangular. What do we use for the exponential distribution that is our burn time? Any thoughts? Yes? Okay, I thought I was muted and not muted, right? What did we learn last lecture for sampling a exponential distribution? What's the second method we learned for sampling a random variable? I mean, the first method we learned is acceptance rejection method, right? What's the second one?
Inverse CDF.
Yeah, it's called the inverse CDF method, right? And what's the idea behind the inverse CDF method? So yeah, we have to look at the CDF first. So the CDF as a function of t is going to be something different from the PDF, right? So it always starts with 0, and it always ends with 1. And for the exponential distribution, the CDF is also exponential, except for it approaches 1 exponentially. So how do we use the CDF, and particularly the inverse CDF, for sampling such exponential distribution? Well, the idea is we are going to be uniformly sampling the y-axis of the PDF, and then use the inverse of the PDF to map it to the x-axis, which is t. So if we sample with uniform bins along the y-axis and we map it back, we're going to see that when the CDF is steep, the bin on the x-axis are narrow, so we get denser samples over there. When the CDF is shallow, the same width of bin in the y-axis gets mapped to a wider region in the x-axis. So the samples are less dense in these regions. All right, and essentially we sample y, that is a uniform 0, 1 distribution. So this is U. And we use the inverse CDF. So the inverse CDF in this case is what? It's going to be, so let's actually write down the CDF. So the CDF of t as a function of a small t is going to be an exponential, always going to be 1 minus an exponential of minus lambda t minus 55. All right, so that means if this is y, right, then 1 minus y is going to be exponential of minus lambda t minus 55. And my t is then going to be 55. It's going to be 55. Well, let me write it down more clearly. So if we take logarithm on both sides, log of 1 minus y, it's going to be minus lambda times t minus 55, right? And the log of 1 minus y divided by minus lambda is going to be t. It's going to be t minus 55. Okay, so we know that if we sample uniform on y, then I can compute my t being 55 minus log of 1 minus y divided by lambda, which is 1 over 5 seconds. Okay, so let's do let's plug this formula into MATLAB. So again, we're going to be sampling another y. Let's call it yt. Is going to be rand of n samples, and my t is going to be 55 minus log of 1 minus yt divided by lambda, which is multiplied by 5, right? And let's now let's make a subplot 2, 1, 1 here, and another subplot 2, 1, 2 here, and hist t with 100. All right, so now we have two distributions, one triangular and one exponential. That's our burn time. So we have completed our first task of sampling the distributions.